Okay, I just want to pick up where we left off. We were talking about the variance and what it essentially means. Once again, the variance is going to be just how much the data is varying. So, visually, this is going to be the variance. Now, quick recap of the expectation concept. The expectation of x is going to be if we observe x a million or like an infinite amount of times, what can we expect to get? So, for example, let's take the die roll again, six-sided die. We can get 1, 2 through 6. So the expectation of the die roll is going to be if we roll the die an infinite amount of times, what are we going to get? And it usually is the mean or the average value. And I think we computed this average to be 3.5 or something like that. So that is going to be the expectation of the die once you roll it many times or an infinite amount of times. The expectation concept, I hope, is clear by now. It's basically what do we expect the value to be, and it usually is the average. Let's just quickly look at the expectation function. So say we have a random variable x, and the true mean, the true average of the random variable is going to be mu. We have an estimate which is going to be 1 by n summation 5 over n, and then we just add up all the x's and then divide it by the total number of x's. We've already done this before, but I just want to quickly apply it. So the EF x bar, it's going to be EF, we're going to substitute it in 1 by n x. We already discussed that the expectation of a constant is going to be the constant itself, so we pull that out. We also discussed that if you have summation inside an expectation, you can pull the summation out. So in other words, E of a summation of a certain variable, say z, is going to be the same as summing the expectation of the variable z. So instead of finding the expectation of the whole z value added together, you can find the expectation of the z value and then add it all together. So based on this, we can pull summation out, then we get E of x. Since we already know that the true mean of x is going to be u, this also implies the expected value of x is going to be mu. Because again, E of x is usually, or rather almost always, the average, the true mean. So with this in mind, we can just substitute in mu for E of x. This just becomes into n mu, because again, I think we discussed this before, but like adding up, so let's say mu is equal to 5, adding up 6 times is the same as saying 6 into 5. So adding up something n times is the same as saying n into that number. So we can just substitute that in, cut this out, and we get mu. So that's just how we apply the expectation function. Again, remember, constants just come out, summations just come out. There were some of the rules that we discussed, such that E of x into y is not equal to E of x into E of y. Same with division, but at the same time, E of x plus y is going to be E of x plus E of y. So these are the rules we just need to remember. I just want to do a quick recap. Now, moving on to what we are going to be getting into now is the variance. We already know what the variance is, but I want to show you how the variance function is applied. Okay, so if you remember in a previous discussion, we said that the variance of x is gonna be the same as the variance of x plus some constant c. The reason we discussed this was to show that constants, adding or subtracting constants, does not change the variance. In other words, a variance of c is 0. Why is that? Because c is a constant. So if you plot it, it's just going to be like this, and there is no variance for this. It's just going to be one single observation. So first rule we need to remember is that constants do not have a variance. Okay. Now that we got that, what is the variance of x? Just like we said, any random variable. I'm gonna change up the letters for simplicity to not get it too confusing. Let's say there's a random variable w. Okay, we have an infinite random w, so it can be 1, 92, 73, blah 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 blah. They go all the way, and there's so many. I can't erase for some reason. All right, it's like infinite observations of the value w. Now, in the total population of w's, sorry, my iPad is acting up a little. Total population of w's is going to be 1 true mu. That's going to be the true average. We add up all the w's and we get the true mu. That's going to be the mu, which is the true average, or rather the mean. Same thing, but usually we prefer using the word mean, I think. Just like it has one true mu, one true parameter mu, it's also gonna have what we call a theta square. Okay. What is a theta square? The theta square, we need to remember this notation, just like we need to remember mu. The theta square is the true variance of w. So the same thing, we're gonna plot it on a chart, and then we're gonna find the true variance, and that true variance is denoted as theta square. Now, we need to remember this, that any random variable, right? Any random variable, to understand how each random variable is distributed, the nature of each random variable, we need these two set of informations. The mean tells you, the mean tells you what's the average, what's the center point, and the variance tells you how spread apart the data is. So if the mean is 0 and the variance is like 2, the data is going to look something like this. If the mean is 20 and the variance is like 300, it's going to look like this. Usually spread apart and kind of centered around 20. So again, for every random variable, to understand it, we need to know the mean and the sigma square. Just a second, I feel like I'm confusing my Greek letters. Let me just check. Is it theta or sigma? Yeah, sigma squared, sorry. So we need to know the mean and the variance, the mu and the sigma square. Now it is going to become clearer once we get into an example. Okay, so we know that each variable has a true variance and a true mean. So usually at the question we're going to be given the variance of x is sigma square. So when we apply the function variance of x, we're going to get sigma square. If we are asked what's the variance of x plus 7, it's still going to be sigma squared, like we said, because a constant does not have variance. Now, the rules of variances and expectations are very similar in some ways, in that you can break this down like this. This rule applies, and the same with this rule. Both rules do apply. We know the variance of x is sigma squared. We know the variance of 7, because it's a constant, is 0, equal to sigma squared. Okay. What about the variance of 6x? Like with expectations, we can take the constants, any constant multiplication, out of the variance. But if this was e of 6x, we would do 6 into e of x is equal to 6 mu. If it is e of x plus 6, it would be e of x plus e of 6 is equal to mu plus 6. Before we get to this, I just want to show you something. But we know if it's the variance of 6 plus x, we're going to break it down. But we know this is 0, so we're just going to get sigma square. So it works differently here, because e of 6 is going to be 6, but the variance of 6 is going to be 0. The expectation of a constant is the constant, but the variance of a constant is 0, because a constant does not vary. Okay. With the variance of like multiplication, it's going to be slightly different. Rather than pulling it out, simply, when we pull it out, we're going to have to square it. So when this comes out, it's going to be 36 variance of x is equal to 36 square. Now, I don't want to get too much into the intuition of it, but if you want to have a very shorthand way of remembering it, you can just remember the variance has a square up there inherently. So when you take something out of a variance function, you just remember to square it. Okay, so these are like the baseline rules that we need to know now. When we encounter bigger questions and bigger problems, I'll show you how we can tackle those. Now, let's quickly go back up to the question that we were dealing with. Can I copy it? Okay. Let's try and apply all the stuff we've learned. Okay. Theta hat 1, theta hat 2 are two unbiased estimators of theta. Okay. Now let's first quickly write down what this information means. If they're unbiased, we know that we expect theta hat 1 to be theta. We expect theta hat 2 to be theta. Because again, unbiasedness basically means if you do it a million times, you're going to get the right answer. And another way of remembering it is bias is equal to bias of a certain let's say theta hat 1 is equal to E of theta hat 1 minus theta, which is what we're trying to get. And if this is equal to 0, that means these are equal to each other. Okay, but again, you don't need to do all of this here. You just need to write this down. Okay, what's the next information that we have? Theta hat 1 and theta hat 2 have the same variance, sigma squared. So variance of theta hat 1 sigma squared, variance of 2 is equal to sigma squared. Okay, another two possible estimators of theta are theta hat 3, let me switch up, and theta hat 4. Okay, which one of these estimators is the best and which one is the worst based on the mean squared error? Explain your answer. Okay, so we want to do it based on the mean squared error. We know MSE of any estimator is going to be the variance of the estimator plus bias of the estimator squared. Okay, let's start working it out. So they want us to first do it for theta hat 1. Okay, MSE of theta hat 1 is equal to be the variance of theta hat 1 plus the bias of theta hat 1 squared. We know the variance of theta hat 1 is sigma squared. Bias, we know it's unbiased, so there's going to be nothing there. So the MSE of theta hat 1 is simply sigma squared. Let's go to theta hat 3, which is theta hat 1 minus theta hat 2. Okay. Let's start by working out. So we want to find the bias and we want to find the variance. To find the bias, we've already done this before, and we know we need to find the expected value. So expectation of theta hat 3 is going to be expectation of theta hat 1 minus theta hat 2. You know, we can break this apart. Theta hat 2. From here, we know both expectations equal to theta and theta, so 0. So the expectation of theta hat 3 is 0. So to find the bias, we're going to go bias of theta hat 3 is equal to expectation of theta hat 3. What do we get when we use it? Minus what do we want to get, which is theta. So it's going to be 0 minus theta minus theta. Okay, that's a bit disappointing. Clearly it's not unbiased. It has a bias of negative theta to it. Let's work out the variance. Okay, so we haven't done the variance before in the setting, but let's quickly figure out how to do this. So variance of theta hat is going to be variance of, you just plug in what theta hat 3 is. Okay, like I said, we can break this apart. 1 minus variance of, wait. Okay, when you break it up, for now let's just think of it as minus 1 here, which is the same when you say theta hat 1 minus theta hat 2, which is the same as saying theta hat 1 minus 1 into theta hat 2. I'll show you why I'm doing this. So when we break them apart, we just separate them. Variance of minus 1 into theta hat 2. Now we want to take this constant out. We don't want to have this minus 1 inside theta inside the variance function, so we take it out. But remember, when we take a constant out of the variance function, we are going to square it. So when we square it, it becomes positive. So it's going to be plus 1 into variance of theta hat square. It's basically variance of theta hat 1 plus variance of theta hat 2. Now basically what I want to tell you is, if you have something like variance of A minus B, it isn't going to become variance of A minus variance of B, because when you take this, when you break apart them, you need to remember to square this minus, and when you square a minus, it's going to become a plus, so it's going to be like this. Remember, it's never going to be variance of A minus variance of B. Intuitively, if you want to think about it, like say you have two variables, blah 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 blah, and you're trying to find the variance of their difference. If you subtract them, you're going to end up with a lower variance than it truly is. So you just add them up. Again, this might not be the clearest intuition, but just remember, if you're breaking apart the variance, you always need to have a plus sign. You always add up variance together when you do it like this. And I think it helps if you think of it like this. If you have minus in there, just remember to square it when you bring it out. In other words, variance of A minus B is going to be variance of A plus variance of B. Okay. With that established, let's just go up. We know variance of theta hat 1 is sigma squared, variance of theta hat 2 is sigma squared, so it's going to be sigma squared plus sigma squared, will be 2 sigma squared. Okay, now finally we need to calculate the MC of theta hat 3, which is going to be 2 sigma hat squared plus, we need to square the bias. We know the bias is minus theta, so minus theta into minus theta is going to give us theta squared. So this is the MSE of the third estimator. Let's quickly do the same for the fourth. Theta hat 4 is equal to theta 1 by 4 plus theta 2 by 4. Okay. Again, we start with the expectation. I'm just going to break it apart already just to make it a bit quicker, because it's taking a bit of time. Like I said, you know what we do here? We're going to pull out the constant. It's going to become 1 by 4 to E of theta hat 1 plus 3 by 4 into E of theta hat 2. We know both of this is theta, so it's going to be 1 by 4 theta plus 3 by 4 theta equal theta. So we actually do get theta here. The bias obviously is going to be theta, since we got this here. This is the E of theta hat 4. Theta minus theta is going to be 0, so it is unbiased. That's good. Okay, let's quickly look at the variance as well. Variance of theta hat 4 is going to be variance of theta hat 1 by 4 plus variance of 3 theta hat 2 by 4. Again, remember, when we take out the constant, in which case is 1 by 4, we are going to square it, so it's going to become 1 by 16 variance of theta hat 1 plus 3 by 4 squared is going to be what? 9 by 16 variance of theta hat 2. Okay, let's add this up. It's going to be 10 by 16. So we know this is sigma squared. Sigma squared. You can simplify this. 5 by 8. 5 by 8 sigma squared. Okay. Now let's write down the MSE, which is what we are trying to compute. The variance is 5 by 8 theta squared. We know it's unbiased, so it's going to be 0 squared, which is 0. Okay, so now we have 3 MSEs. So this is MSE of theta 4, MSE of theta hat 3 is going to be 2 sigma squared plus theta squared. MSE of theta 1 is going to be simply sigma squared. I think that's what we got. Yep. Okay. Now, like we said, we want the lowest MSE. From here, it's obvious that the lowest MSE is this, because it's obviously not this, because this is 2 sigma squared, while this is sigma squared, so it's going to be second one, and this is like about half sigma squared, so 3. So from here we can finally say which estimator is best. We can say theta hat 4 is the best, theta hat 1 is alright, theta hat 3 is the worst based on the MSE. Okay, so this is how we take down this problem. I'm sorry this is a lot, but it's fairly simple once you get to do it. You just need to take every estimator, compute the bias, compute the variance, which we saw here, do it for every estimator, calculate the MSE by just adding them up and adding the variance in the square of the bias, and then just order them on the basis of the MSE to find the best and the worst estimator. This is guaranteed 10 marks, and combined with figuring out this proof, I think it's going to be 6 or 7. It's already like half our goal, so I really recommend you try and get a lot of this done. Let's quickly see if we want to do. I'll come back with another question. Okay, so I just wanted to tackle another way that this question can appear. So usually, like 9 out of 10 times, you're gonna either get a question of this type, where they just tell you theta hat 1 is unbiased, theta hat 2 is unbiased, this is the variance, go and figure out what is the best estimator. Sometimes you might get something like this, where they give you the random variable and the possible values you can take, and then ask you to compute which estimator is better or unbiased also. Okay, so if we know how to solve both these types, we should be covered most of the times, so that's why I want to do this. Okay, so we have random variable x that can take 3 possible values, so 0, 1 or 2. The probability that it takes 0 is going to be 1 minus 5 alpha by 8. Okay, alpha is some variable. Oh wait, okay, I'll get the probability that it takes 1 is alpha by 4, probability that it takes 2 is 3 alpha by 8. Okay, one observation is taken and we want to estimate alpha. Okay, so we want to figure out alpha. Alright, consider the estimators. The first one is just the one variable of x. T2 is 4 by 3x multiplied by the value of x minus 1. Okay, and we want to show that both are unbiased estimators of alpha. Okay, so this looks quite complex to start, but it's actually simple as we break it down. When we want to prove unbiasedness, we want to focus on the expectation, right? So we want to find the expectation of T1, and we want to show that is equal to alpha, so that we can say that T1 is unbiased estimator of alpha, which is what they're asking us to do. Okay, expectation of T1. Let's go back to the example we had when we first started, the expectation of a die. What did we do? We took, so there are 6 values that a die can take. So for each value, we multiplied the probability of getting that value into the value itself. So it looked like 1 by 6 into 1 plus 1 by 6 into 2 plus 1 by 6 into 3 and so on, and then we just sum it up and we get the E. Okay, now E of t1, what is t1? T1 is equal to x. Okay, so we want E of x. We know x can take 3 values. Okay, so E of x is going to be, what's the probability that x takes 0? 1 minus 5 alpha by 8 into 0, which is the value it's taking, plus alpha by 4 into 1, which is the value it's taking, plus what's the probability that it takes 2? 3 alpha by 8 into 2. So E of x is going to be, of course this goes to 0 because it's multiplied by 0, alpha by 4 plus 6 alpha by 8. We can just multiply this one by 2, both the top and the bottom, the standard multiplication, add them up, and we get 8 alpha by 8, the 8's cancel out, is equal to alpha. Okay, so E of t1, which is equal to E of x, because t1 is just x, is equal to alpha, and alpha is what we're trying to find, so it is in fact unbiased. Let's do the same for E of t2. E of t2 is going to be E of 4 by 3x into x minus 1. Okay, E of 4 by 3x into x minus 1 is going to be, what's the probability that it takes that it takes 0? It's going to be 1 minus 5a by 8. So we want to put 4 alpha x minus 1. Just a second. Okay, I just paused to make sure that this is explained as clearly as I can. Okay, so we are trying to, our estimator is going to be 4 by 3 x minus 1. So we know x can take 0, 1 or 2. So when x takes 0, the value we're going to get from our estimator is going to be 4 by 3 into 0 into 0 minus 1. This 0 basically makes everything 0. Okay, so when x is 0, we're gonna E of t2. When x is 0, we're gonna get 0, and the probability of getting that 0, or rather the probability of x being 0, as we saw here, is 1 minus 5 alpha by 8. Okay, second, we can get our x as 1. So 4 by 3 into 1 into 1 minus 1 is equal to 0, because 1 minus 1. Okay, so if the x happens to be 1, our estimator is going to give us a value of 0. So plus 0 into, what's the probability of x actually being 1? Alpha by 4. Okay, what if x is actually 2? In this case, we are gonna get I can't do quick math for some reason. We're gonna get 8 by 3, because this goes to 1 and just 4 into 2 by 3. Okay, so if x is 2, we're going to get our estimator is going to give us the value 8 by 3, and the probability of x being 2 is 3 alpha by 8. So since there's 0 here, this goes to 0, this goes to 0, it's just going to be this. So E of t2 is going to be 8 into 3. Oh wait, you can just cut this. It's going to be alpha. Now, just so making it clear, basically what we're doing is we're saying we have two estimators, and each time we use the estimator we're going to get a different value, and we have three possible values of x that can be taken. So we're just computing, if I get the first value of x, what is my estimator going to spit out, and what's the chances that I get that value? If I get the second value of x, what is my estimator going to spit out, and what is the chance of it? In the first example, it looks very simple because the estimator is just x itself. But in the second example, we see we have to calculate, if I get 0, my estimator is going to give me 0. If I get 1, my estimator is going to give me 0. If I get 2, my estimator is going to give me 1. And then we multiply it with the probability of the value itself. So what's the chance of getting 1, what's the chance of getting 2, what's the chance of getting 0, and if I get those values, what is my estimator going to give me? Okay, I hope that was clear. So that way we showed that this is unbiased. Okay, since both estimators are unbiased, and we know MSE is equal to variance plus bias squared, since that's basically not there, our focus is just going to be on minimizing the variance. The one with the lowest variance is going to have the lowest MSE, and it's going to be the better the preferred estimator. Okay, to do the variance in this situation is going to be a bit different. Let me just move this down actually. Okay, so if you remember in the previous style of question that we attempted, we were given the variance. They said it was sigma square. Here, unfortunately, we don't get the variance. We only get the probability of x taking different values and the estimators themselves. We already know they're unbiased, and we want to calculate the variance to show which estimator we prefer. Now, here's where the formula that we discussed in the last video is going to come in very handy. If you remember, variance of x is nothing but e of x squared minus e of x squared. Okay, the thing is, we already know what e of x is. Or rather, let me put it into context. So to find variance of t1, we just need to find e of t1 squared minus e of t1 the whole square. We'll get to this. I mean, the same applies for t2, by the way. We'll get to this, but we already know this. Since it's unbiased, we know e of t1 is nothing but unbiased estimator of alpha. E of t1 is nothing but alpha. So we got this bit sorted. We just need to work this out. Okay. E of t1 squared. Okay. So we're going to get our value of t1 and we're going to square it. We're going to get a value of t2, then we're going to square it. Okay. T1, when x is equal to 0, is 0. Actually, let's do it. Let's draw a little table. T1 is equal to x from here. So when x is equal to 0, t1 is going to be 0. X is equal to 1, t1 is going to be 1. X is equal to 2, t1 is equal to 2. What about t1 squared? T1 squared is going to be what? X squared. This is going to be 0, this is going to be 1, this is going to be 4. Okay. So we know for each value of x what t1 squared is going to give us. Now we just rinse and repeat. We just take these values of t1 and multiply it with the probability of x being the associated value that gives us this value of t1. Okay, sorry if that sentence was a bit complex, but as I work it out, I think you'll be able to see. So expected value of t1 squared is going to be nothing then. What's the probability of x being 0? Which is 1 minus 5 alpha by 8. I'm just looking at this. Multiplied by, if x was 0, our t1 is going to give us 0. Okay. We're going to do the same for what's the probability of x being 1. And if x is 1, we're going to get the value of 1 from our t1 squared. Plus probability of x being 2, which is 3 alpha by 8. And if x was 2, our t1 is going to give us a value of 4. Okay. This goes to 0. So e of t1 squared is simply going to be alpha by 4 plus 12 alpha by 8. It's going to be 2 alpha by 8 plus 12 alpha by 8. 14 alpha by 8 is going to give us 7 by 4 alpha. Again, you can simplify this however you want, but I just like doing it like this. I just multiply them both by a number to get it the base same, and then I just add them up and simplify. Okay, so e of t1 squared is 7 by 4 alpha. Again, we're trying to find the lowest MSE. MSE is equal to variance plus bias squared. From the previous question, we know they are unbiased, so we don't care about that. So we're just trying to find the variance, the one of the lowest variance. So to find variance of t1, we just do e of t1 squared minus e of t1 the whole square. So e of t1 squared is 7 by 4 alpha minus e of t1 we know is alpha, square it, alpha squared. So this is the variance of t1, and because of this is also equal to the MSE of t1. 7 by 4 alpha minus alpha squared. Okay, let's quickly do the same for t2. So it's going to be the same. Variance of t2 is going to be e of t2 square minus e of t2 the whole square. We already know e of t2. Let's just focus on e of t2 squared. So when x is equal to 0, what's t2 again? t2 is 4 by 3 x minus 3. Minus 4 by 3 x minus 1. Yeah, okay. And t2 is going to be 4 by 3 x minus 1 the whole square. But we don't need to work this out because we can just take this value and square it. Okay. When it's 0, we're going to get 0 because, when it's 1, when x is 1, we're still going to get 0 because 1 minus 1, this goes to 0, and that takes the whole thing down. When it's 2, we're gonna get 8 by 3, right? From the previous part, we can just um, steal it, probably. Yeah, 8 by 3, okay. Now, t2 squared, so I forgot to draw square there. For t2 squared, we can just simply square this thing, 0, 0. It's gonna give us 64 by 9. Looks a bit complex. I feel like I've messed up a little bit here. It's gonna be 2 minus 2, 8 by 3, 64 by 9. Yeah, looks right. So it's gonna be 64 by 9. Now, again, to find the expected value, we're just gonna go e of t2 square. Probability of x being 0 is gonna be 1 minus 5 alpha by 8 into 0 plus alpha by 2. I'm sorry if my handwriting is deteriorating, but this doesn't really matter because we know it's going to be 0s anyway. 0 plus 64 by 9. Actually, let's do that. The probability of getting x is equal to 2 into what value of t2 square we get when x is equal to 2. Okay, so we can write this down. We can simplify. Oh damn it. Okay, 1, 3. This is gonna be what? I should know this. 8, 1. Okay, that gives us 8 by 3 alpha. Okay. Now the last step, don't forget, compute the compute the variance. Variance is this. We just figured this out, 8 by 3 alpha. 8 by 3 alpha minus, we know e of t square is alpha, so alpha squared is going to be alpha squared. Okay, so we got the two variances finally. We also know this is the MSE because, again, no bias. So let's compare 8 by 3 alpha minus alpha squared versus 7 by 4 alpha minus alpha squared. At this stage, you just pop it into the calculator. I mean, if you're able to just look at the numbers and tell which is bigger, then that's great. I'm just going to quickly pop it into the calculator, and 7 by wait, you don't need to pop it into the calculator. I'm just being dumb because you have a larger numerator and a smaller denominator, so obviously this is larger. But yeah, again, it's not necessary. So this is obviously smaller. This is t1, t2. So variance of t1 is smaller than the variance of t2, which also means MSE of t1 is smaller than the MSE of t2. Therefore, we prefer t1. There we go. Okay, now I know that was a lot taken, but just to recap, when you're dealing with a question like this, all you do is look at the estimator, figure out for each value of the x what value you'd get from the estimator. So, and then just multiply the probability of getting that value of x with the value you get from the estimator. So multiply the probability of getting 0 into what value you would get for that estimator if x was 0, and do it for all the other values of x and just add them up. For finding the variance, what is the probability of getting 0 multiplied with what would I get if x was 0 and then I squared the whole thing. Easiest way to do it is just make a table. You have your estimated value and then you just square it, estimated value, square it, and then you just add that up. You get your E of t squared, and using E of t squared, using this formula, variance of is equal to E of x squared minus E of x squared minus E of x the whole square. You can work out the variance, calculate the MSE, and tell them what estimator you prefer. Okay,